If a big asteroid were on a collision course with Earth, we may try to intercept it and change its course. For this mission, the interceptor would have a guidance computer programmed with an advanced guidance law, such as one derived with optimal control. Optimal guidance laws, whether for asteroid interception or other targets, often depend on a quantity called time to go. In this lesson, we investigate how to estimate this important variable. Time to go is employed in a guidance homing loop that involves the engagement kinematics of the target and pursuer, or interceptor. That kinematic data is fed back with two main types of sensors. One is the inertial measurement unit. It's onboard the pursuer, measuring its acceleration and angular rates. Additionally, there's a remote sensor, whether it be onboard the pursuer, like a seeker, or external, such as from a satellite. These measurements are input to a state estimator that outputs data for guidance law operation. Here we have an optimal guidance law that requires time to go. The guidance law commands motion of the pursuer, such as its acceleration. The controller receives the command, produces control effector commands, and the interceptor receiving those effector commands executes them through its control actuation systems. If all goes correctly, the desired motion is achieved, and the pursuer intercepts the target. Here, our goal is to develop methods of time-to-go estimation toward application of optimal guidance laws. For example, linearized proportional navigation is optimal in the sense of minimizing control effort when the navigation gain is 3. This law directly depends on time to go and on zero effort miss perpendicular to the line of sight, which will be discussed later. So what exactly is time to go? Well, in short, it's how much time is left. That is, time left at the present time, t. It's computed as the difference between the final time, or the time when intercept happens, and the present time. Suppose we know the interceptor state at time t, and we wish to know at what future point in time, tf, it will intercept the target. If we knew exactly how the interceptor would approach the target, this would not be difficult. But the target, the pursuer, and their environment all have uncertainty, so that tf is unknown. And this is our challenge, to estimate time to go despite not knowing what will happen in the future. We estimate time to go point-wise in time. So suppose we're at the ith point in time, ti, and the final time is unknown, so the actual time to go is unknown. Our present goal then is to obtain an accurate time to go estimate at ti. Now, suppose time has advanced to ti plus 1. Our time to go estimate is now at ti plus 1, and we would like to be more accurate than before. And at ti plus 2, we would obtain an updated time to go estimate with even greater accuracy. This continues until we reach an estimated time to go of 0. That is, we are at the final time. Each time we estimate time to go, we are making a prediction of when a future event occurs. In essence, this is extrapolation, which in engineering can be a dangerous thing to do. But we don't need to be a mystic to make these predictions. We can use present measured data related to our kinematics to estimate the future to a reasonable degree of success. Consider our pursuer with an attached coordinate system and the target also with a coordinate system. The target and pursuer will have instantaneous velocities and instantaneous accelerations. Let these quantities and their positions be resolved in an inertial coordinate system with their instantaneous positions and relative position defined. The time derivative of relative position gives relative velocity. That is, the difference between the instantaneous target and pursuer velocity vectors. And the derivative of relative velocity is relative acceleration. Similarly, the difference between the target and pursuer acceleration vectors. Starting with this instantaneous relative acceleration, and assuming for the moment that it does not change going forward in time, we will integrate relative acceleration with respect to the placeholder variable tau to get relative velocity as a function of the elapsed time going forward, tau. This is simply relative acceleration times tau plus the constant of integration, which is just present relative velocity. We also note that relative velocity is the derivative of relative position. So we can get to relative position after elapsed time tau with one more integration. Substituting relative velocity as a function of tau in for r dot, we get then a quadratic formula in terms of tau. Now, evaluate relative position after time has elapsed from the present time t to the final time tf. Since t minus tf is just time to go, we get an equation for relative position as a function of time to go. It relies on present relative position, present relative velocity, and present relative acceleration. And it gives a prediction of future relative position after the remaining time to go has elapsed. As such, we will call this the relative position equation. This equation is the basis for 3 time-to-go estimation methods that we will derive in this lesson. To start, we note that for target interception, we desire relative position to be 0, so that after time to go has elapsed, we desire the pursuer and target to be at the same point in space at the final time tf. Note that when applying this equation at a point in time, relative acceleration, relative velocity, relative position are held constant. But when applying this equation to a sequence of points in time, these relative quantities are updated at each time step. At first glance, we may be tempted to use the quadratic formula, but it's not so simple because each of these parameters are three-dimensional vectors. So when we write them out for each coordinate direction, we get 3 equations with the single unknown time to go. So to solve for time to go, we first bring present relative position to the right-hand side, then factor out time to go on the left-hand side. And we'll take the vector 2 norm of each side. Note that time to go is a positive definite scalar. And the 2 norm of present relative position, it's simply range. So, by taking the norm of both sides, we get a scalar equation in terms of time to go. We can now write this as an implicit equation in terms of time to go. And this is our first main result for time to go estimation. But note, it will require iteration because it's implicit. It also requires range, and of course in the denominator, relative acceleration and relative velocity resolved in the inertial coordinate system. That data has to be known at each time step to use this equation. The complexity of the former result greatly simplifies if we assume negligible relative acceleration. Then, what's in the norm on the denominator is just relative velocity. Note that the present relative velocity vector is not necessarily along the line of sight. But if we assume this is approximately true, then we can substitute the relative velocity norm with the range rate. As range should be decreasing, note that range rate is negative, and relative velocity magnitude is positive. So our approximation is minus the range rate. And minus the range rate is closing velocity, since VC is positive by definition when closing in on the target. Bringing this approximation into our time to go formula, we substitute for minus r dot in the denominator. This is equivalent to r over closing velocity. And this formula is our second main result, another method to estimate time to go. To arrive at this result, we focused on quantities resolved along the line of sight. So what if we were to go back to the relative position equation and resolve it only along the line of sight? This leads to our next estimation formula. To project the kinematics onto the line of sight direction, we'll define a new coordinate system with a coordinate direction along the line of sight 1r. You can call this a line of sight coordinate system. We divide relative position, resolved in an inertial coordinate system, by range to get the coordinate direction 1r. Now, taking the dot product of both sides of the relative position equation with 1r, we get a new right-hand side where we have instantaneous range rate, or minus the closing velocity, denoted here as simply v, and instantaneous relative acceleration along the line of sight, denoted a. Thus, our vector equation simplifies to a scalar quadratic equation. We can directly solve for time to go with the quadratic formula. Since the quadratic formula has two solutions, let's briefly examine their terms here to identify when they may be valid. We'll make the assumptions that range is positive, range rate is negative, and range acceleration is positive. Through trial and error, we find here that these assumptions hold. And with these assumptions, this solution is valid. Since time to go is positive, definite, and real, and we have on the right-hand side a positive square root term that's subtracted off, it seems like this chosen solution could lead to negative time to go. Let's look a little further. The first term, minus v over a, is positive by our assumptions. The second term must be real and therefore positive. V squared must be greater than 2ar, which is true in our simulations here, we find, but not necessarily guaranteed. If you consider a slow-moving engagement but with high acceleration at short range, this could provide complex time to go values, and for both solutions to the quadratic equation. At this point, it's unclear how the resulting complex time to go estimate may be related to the actual time to go. This question is not examined further here. Now, if time to go is positive, then the first term has to be greater than the second term. Squaring both sides, then subtracting v over a squared from both sides, we get that r over a must be positive for time to go to be positive. And we know that r is always positive unless at intercept. So this reduces to the requirement that the pursuer and target must always be accelerating toward each other for a positive time to go estimate. This was part of our initial assumption. The selected equation is the third time to go estimate method considered in this lesson. And while you see it works, the result is heuristic and does not imply a guaranteed useful time to go estimate. Further analysis of this result is needed to fully understand the validity of this approach for time-to-go estimation. Before simulation, let's summarize our results. Our first estimation method does account for relative acceleration, but on the downside, it's implicit and requires iteration to solve, such as with a Newton-Raphson root finder. Further, it requires instantaneous measurements of velocity and acceleration resolved in an inertial coordinate system. Our second estimation formula was derived from the first formula. On the downside, it does not account for acceleration, and it also assumes relative velocity magnitude is approximately closing velocity. On the plus side, it's simple. It requires minimal data, all resolved along the line of sight direction, and it's explicit. The third estimation formula is motivated by resolving the time-to-go estimation along the line of sight direction. This results in an explicit formula that accounts for relative acceleration. The result appears to be valid under certain kinematic assumptions that are not necessarily guaranteed. If you have a reference that discusses this further, please put it in the comments below. With these methods, we're now ready to test the accuracy of each approach. We'll simulate various engagements with proportional navigation, get the actual time to go, and use the simulation data to estimate time to go for each method. For this, perfect kinematic data is fed back in the simulation so that the relative motion history is obtained. Then, each time to go estimation formula is applied and compared to the actual time to go. The procedure is as follows. First, define engagement initial conditions. Then, simulate the engagement, store the results. Next, compute actual time to go. Then, for each estimation method at each time step, compute and store the time to go estimate. For the iterative method, a Newton-Raphson algorithm was applied and 10 iterations were executed at each time step. The initial guess is the previous time to go, except at the first time step where the method R over VC was used as the initial guess. Finally, time to go estimates and their errors are plotted and compared. Here again are the estimation methods we derived here. They are referred to as methods A, B, and C in order of their previous development. We will now examine each method in a series of engagement examples. In this first example, we run true proportional navigation, which is normal to the line of sight direction. We have an initial closing velocity of approximately 4,000 feet per second, where the bodies are separated by 40,000 feet. These bodies would be on a collision course if it were not for the pursuer heading error of -2 degrees. The target does not accelerate. Offhand, we'd expect an initial time to go of approximately 10 seconds. This is a simple case where we would expect all methods to do well. The pursuer turns into the target requiring minimal acceleration with small line of sight rate and line of sight angles. This is essentially a head-on collision. We now plot the time to go estimates for each method in order of their development on top of the actual time to go. At first glance, it looks like everything is working perfectly until we notice that method C appears to be on the zero axis. Zooming in on time to go lines, we observe that actually only the implicit method A that accounts for relative acceleration and the simple explicit method B that does not account for relative acceleration are there. Indeed, method C has failed. Plotting the error signal between the actual and time to go estimates, we observe an intermittent signal in method C with large errors that then decrease. Methods A and B produce excellent results as we saw earlier, converging to near 1e to the -4 seconds. We'll address the failure of method C shortly. We might expect method A, which accounts for relative acceleration, to be more accurate than method B, which does not. But initially, we see the opposite is true. This is attributed to the assumption of constant relative acceleration. Although the relative acceleration is updated at each time step, it's assumed constant, so that early on it's a greater source of error than improved accuracy. In addition to absolute error, it's also interesting to examine relative error, which is essentially absolute error normalized by time to go. If we were to multiply by 100%, this would just be percent error. We see methods A and B are accurate to within 1 part per thousand, up to the last fraction of a second, where we observe the relative error diverge. The reason is that the numerator converges to approximately 1e to the minus 4 at about 5 seconds, just as we saw. But the denominator, the actual time to go, continues to decrease to 0. Finally, you may have noticed method C at 1 at the top of the plot having 100% error. Recall that method C has relative acceleration along the line of sight in the denominator. Since true proportional navigation commands acceleration normal to the line of sight, and the target does not accelerate, there is no relative acceleration A in the line of sight direction. As a result, the denominator is 0, and the numerator reduces to 0 in the method C formula. In Octave, this produces an intermittent signal of zeros and nans, where the zeros were appearing in the plot. The failure of method C here requires both the target not to accelerate and the use of true proportional navigation. This highlights the importance of considering the suitability of the engagement kinematics with the time to go estimation method. As a measure of total error for each method, we integrate the relative error from the initial to the final time. We call this the total error, and we'll tabulate the results for each method as we go through a series of examples. We now run the same engagement scenario again, but this time use pure proportional navigation, where the acceleration command is normal to the pursuer velocity vector. That is, there will be a non-zero relative acceleration even though the target does not accelerate. From the trajectory plot, it looks the same, as does the time to go estimate, but now we can see method C overlaid in the plot. The absolute error again converges to near 1e to the minus 4, with the methods containing relative acceleration initially less accurate, but after about 4 seconds they become as accurate as method B. This is attributed to the impact of error due to the constant acceleration assumption decreasing as the engagement nears the final time. The singularities observed in methods A and C are due to the estimate crossing the actual time to go signal, so that they're briefly very accurate during that crossing. The relative error measure tells a similar story, but with diverging error at the end due to time to go in the denominator going to 0. Updating the total error table, all three methods are still 1e to the minus 3 accurate. In this next example, start with a more severe heading error of minus 20 degrees. The target does not accelerate and pure proportional navigation is used. We now observe the heading error more prominently in the trajectory plot, and the performance of each method is observable from the time to go plot, but all appear to converge to the actual time to go as the final time is approached. Again, method B is more accurate than the methods that included relative acceleration. Here's the relative error and the total error. Still, the simple formula, range over closing velocity, outperforms the more complex methods. Now we set the heading error to 0 for an initial collision course, but the target is pulling a hard 3G turn over the full simulation. The trajectory shows the intercept of the turning target. We observe fairly accurate time to go estimation with some differences between the methods. This is best illustrated in the error plot, where now methods A and C, those which account for the relative acceleration, outperform the simple range over closing velocity formula. And the relative error plot shows a similar result. Now the total error methods A and C are roughly half of method B. Finally, we'll add minus 20 degrees heading error to the previous case. In the trajectories, we observe both the effect of heading error and target acceleration. Time to go estimation shows the largest variation from the truth, particularly for the relative acceleration methods A and C. However, these surpass the accuracy of method B after about 3 seconds. The absolute error plot more clearly shows the accuracy of each method, with very similar results between methods A and C. And the relative error plot, a similar story. Now, tabulating the total error, we find that methods A and C are slightly more accurate than method B, particularly for when the target accelerates. The most accurate method for each example is in green. Now that we have an idea of the potential accuracy of these methods, let's simulate the homing loop with zero effort miss proportional navigation, which relies on having a time to go estimate. Recall the linearized proportional navigation guidance law is optimal when the navigation gain is 3 in the sense that it minimizes control effort for intercept. The law requires zero effort miss normal to the line of sight and time to go. Zero effort miss is the miss distance that results at the final time when the pursuer does not accelerate. That is, the pursuer makes no effort. It's a vector quantity that is simply derived from the relative position equation. Here it is, and since zero effort miss means the pursuer does not accelerate, relative acceleration becomes target acceleration. Then the relative position after time to go elapses is the zero effort miss for a constant accelerating target. A coordinate system transformation onto the line of sight coordinate system provides zero effort miss normal to the line of sight, the required input into the proportional navigation law. When normal zero effort miss that accounts for an accelerating target is substituted into the linear proportional navigation equation, the resulting guidance law is actually augmented proportional navigation, which is optimal in the sense of minimizing pursuer control effort for a constant accelerating target when the navigation gain n is 3. Let's simulate the homing loop with the zero effort miss form of augmented proportional navigation. Here our objective is to understand the impact of time to go estimation accuracy on the miss distance. To start, we specify the engagement condition or parameters. For the pursuer, its initial lead angle, heading error, pursuer position, pursuer velocity, and pursuer acceleration. For the target, its initial heading angle, position, velocity, and acceleration, and we also have the navigation gain n. Next, we enter the numerical integration routine. Over a total of n time steps, we update the state vector for the current time step, and we have the achieved acceleration of the pursuer and target as well. From this data, we compute and store the relative position, relative velocity, relative acceleration, normal ZEM, and any other quantities that may be needed for the guidance or are of interest to examine after the simulation. We then compute the acceleration command from guidance, substitute it into the governing equations, and integrate forward one time step. This produces the state vector at the next time step, but we also need acceleration at the next time step. So we feed the acceleration command into a vehicle response model. However, here we assume that the vehicle response is ideal, so that the commanded acceleration is instantaneously achieved, and it's assigned at the present time step. It's instantaneous. In addition, it's assumed then that at the next time step, ti plus 1, we begin with that achieved acceleration. The index then overall is updated to I plus 1, and the loop continues in this way until finished. The simulation results are stored, and the data is post-processed. 2 of our time-to-go estimation methods require relative acceleration, which adds some extra steps to this integration process. To be clear, we start with the time step of the achieved pursuer acceleration prior to the guidance command. The relative acceleration is computed for time-to-go estimation. Time-to-go is estimated and then input to the guidance law. The guidance law produces the acceleration command. That command is assigned to the achieved acceleration because we assume an ideal vehicle response. And finally, the next time step starts at the achieved acceleration of the present time step. Then the process begins again. Present pursuer acceleration before the guidance command, known from the previous time step. Relative acceleration computed. Time to go estimated. Acceleration command calculated. Present acceleration instantaneously achieves acceleration command. And the achieved acceleration is used to start the next time step. We'll now simulate the homing loop using the zero effort miss form of APN, where time to go estimate is fed back and used to calculate zero effort miss normal to the line of sight. Each method will be tested in a head-on scenario where the target pulls a hard 6G turn. Note that 4 different ranges will be examined in this analysis, effectively being a means to change the final time of the engagement. The case of 40,000 feet downrange produces these trajectories. Notice the inflection in the pursuer trajectory that's indicative of the feed-forward action in augmented proportional navigation. The time-to-go estimates all start near 10 seconds, given the initial conditions of the scenario, but the target maneuver is extending the length of the pursuer trajectory path, increasing the final time compared to a non-maneuvering target. We observe that the methods containing relative acceleration more rapidly approach the actual time to go. The absolute error clearly shows the improved accuracy of methods A and C, which are quite similar. The relative error plot prior to intercept shows the initial 20% error reduces to about 0.1%. Integrating the relative error over time, we see that methods A and C are about 3 times smaller than method B's error. For the other ranges, the error of methods A and C are 2 to 3 times smaller than method B, which does not account for acceleration. But when the miss distance is computed, we find that all methods produce very small miss on the order of about 1/10 of an inch. Here the miss distance is determined with interpolation to the point of closest approach, and it's done between the points in time that capture the pursuer and target crossing paths. Based on this result, the time to go estimation accuracy is deemed very high. So let's systematically corrupt the time to go estimation to observe its effect on miss distance. To do this, we take the previous architecture and we add a constant bias to the time to go estimate. This is then fed into the ZEM calculation and into the guidance law. So after the junction, the APN depends on the perturbed time to go. We'll examine the 40,000 foot downrange case first, showing no time to go estimation bias as a baseline. Then we add 1/10 of a second error and observe 2 orders of magnitude increase in miss distance, from 0.1 inches to about 3 inches. Doubling the bias error then triples the miss distance, from 3 inches to just under a foot. For 0.3 seconds bias, we approach 2 feet of miss for all methods. And for 0.4 seconds, we approach 2.5 to 3 feet of miss. The basic trend of monotonically increasing miss with increasing time to go estimation error is expected. In the application of time to go estimation methods, the relative acceleration, relative velocity, relative position, each of these will have uncertainty that propagates into the solution of the time to go, that is the time to go estimation. So the overall magnitude of the resulting error, it's going to depend on the magnitude of the uncertainty of the relative quantities and each of those methods' sensitivity to those parameters. To recap what we've done, we first motivated time to go estimation, then defined time to go. We derived what we called the relative position equation, and then we derived 3 time to go estimation methods. We estimated time to go for various engagements, and then compared the accuracy of the actual time to go to each method. Finally, we tested each time to go method in closed loop guidance with 0 effort miss augmented proportional navigation. What we found was that first, the guidance law should be considered when selecting a time to go estimation method. Case in point, when the relative acceleration was 0 along the line of sight for a non-maneuvering target, it created a singularity in method C. The simple range over closing velocity is surprisingly accurate, even when the pursuer and target accelerate. Accounting for relative acceleration indeed can give a more accurate time to go estimate, particularly when the target is accelerating. Regardless of the method used here, we had negligible miss when considering the time to go estimation error of each method. And so we had to actually add time to go error to reveal the miss distance sensitivity to time to go estimation. In closing, we note that the effect of uncertain measured relative quantities will drive time to go estimation accuracy for each of these methods. All methods considered here used present information for each time step and assumed present relative data was constant to the final time in order to estimate time to go. Of course, this is an incorrect assumption, and there are more advanced time to go estimation methods that can be applied. Access this lesson and more at learngnc.com. And I'd like to thank each of my Patreon subscribers who gain access to all the codes in this analysis, lesson previews, in-depth video discussion, and code tutorials. You make this content possible. Thank you.